Okay, today I'm going to cover a chapter dedicated to the Milky Way, our galaxy. And so I'm going to cover 4 parts here, just talking about how do we know what the Milky Way is, what it looks like, galactic recycling, the history of the Milky Way, and then what's at the center of the Milky Way. So, what does our galaxy actually look like? So, the true size and shape of our Milky Way galaxy is kind of hard to guess from the way it looks in our night sky. Because we live inside the galaxy, trying to determine its structure is like trying to draw a picture of your house without ever leaving your bedroom. So, that's kind of difficult to do. Also, what's making this even more difficult is that our galaxy's visible light is kind of hidden from our view. And so, just recently, we've had technology that can view our galaxy in other wavelengths of light. And then also, obviously, observing our galaxy and comparing it to others. From what we see on the outside, we kind of have a good understanding of the processes that have shaped the Milky Way galaxy. So, some basic parts of our galaxy and other galaxies. I'll start with, well, I guess we'll start with the disk. So our galaxy is a spiral galaxy. It's got arms that kind of form out from the center. And we see that the spiral arms are part of a very, very flat disk of stars that surround a bright center bulge. And then the entire disk is surrounded by a dimmer, rounder halo. In most of our galaxies, bright stars reside in the disk. There are some in the halo, and we'll talk about that as well. So I think I'm going to jump back a slide here. I'm going to talk a little bit about this interstellar medium. So our galactic disk is filled with interstellar gas and dust, and the gas and dust is called the interstellar medium. And this kind of obscures our view when we try to peer directly through it in our night sky. So it's almost like a smog-like obstruction. So if we could view the galaxy from above the disk, we would see that it does have spiral arms. So how do stars orbit in our galaxy? So stars in the disk part of the galaxy pretty much orbit in the same direction with a little up and down bob-like motion. And stars that are found in the halo tend to have random orientations. So it says halo stars travel high above and far below the disk on orbits with random rotations here in this like greenish color. Stars in the disk have this kind of bob-like up-down motion. Bulge stars also have orbits with random orientations. All right, moving on to galactic recycling. So galactic recycling is a process that proceeds in a lot of stages, and so we'll just summarize it as star cycle. Stars are born, remember, when gravity causes the collapse of molecular clouds. They shine for millions or billions of years, with energy produced by nuclear fusion, dying only when they've exhausted their fuel for fusion, when they run out of hydrogen, and then they use helium and they run out of that. And then they ultimately return all of their material back to the interstellar medium during their lives, either through stellar winds, at the death through a planetary nebula if it's a low mass star, or remember, if it's a high mass star, through that supernova. So high mass stars have strong stellar winds that blow bubbles of hot gas. Low mass stars return gas through stellar winds, not as strong as the high mass stars, and then also through that planetary nebula. Now, with a supernova, supernovas can generate shock waves, basically waves of pressure that move faster than the speed of sound. And so a shock wave can sweep up surrounding gas as it travels, creating this like wall of fast-moving gas. And so then when that happens, we tend to observe a supernova remnant, kind of the aftermath of this shock wave. And with it, we see how it compresses, heats, and ionizes interstellar gas that it encounters with this shock wave. So X-rays can be emitted through it, and it can be made from heavy elements. Supernova remnant cools, begins to emit visible light as it expands, and then we have new elements made from the supernova that do mix with that interstellar medium and return in elements to be recycled again. Radio waves can be emitted as well from supernova remnants, and a lot of times they travel near the speed of light. A lot of cosmic rays that we receive or record from space are also from supernova. Okay, some kind of cool things here. So there's a couple different theories, or models, I should say, that deal with supernova explosions. So When we have multiple supernova explosions in a young star cluster and they blow up into the super bubble, kind of into this galactic disk area, I would say like right here, this galactic disk area. And when the supernova, or sorry, when the super bubble that you see here becomes thicker than the disk, hot gas can blow out of it into the halo. This is the halo region. And so the hot gas in the bubble can cool and form clouds, and those cool clouds then rain back down onto the galactic disk. And so they actually call this the galactic fountain model, where super bubbles formed by shock waves of many supernova blow this gas out of the galactic disk. It will cool and rain back down back on the disk. So that's all that's basically shown in this picture here. So then when we have this cooling in going on, raining down back on the disk, it can be cool enough so that hydrogen atoms remain neutral rather than being ionized. And so this gas can be atomic hydrogen gas. It can mix with other neutral atoms of helium and combine with other molecules. So Orion, this is kind of a complex picture of a molecular cloud in the constellation Orion, kind of near the belt region, if you will. And we're measuring the Doppler shifts, okay? So remember with Doppler shifts, you can be red shifted. Red means that it's moving away from us, and blue means it's coming towards us. And so this is a very, very enormous cloud that's stretching thousands of light years across the night sky. Okay, gravity forms stars out of gas and molecular clouds, and it kind of completes our star cycle. So up here, it says radiation from nearby stars is eroding the surfaces of these clouds and causing them to glow, as you can see right here on this border here. But it says, but the densest knots of gas resist that erosion and continue to form stars in other parts of it. So in summary, stars make new elements by fusion. Dying stars expel gas in these new elements, producing hot bubbles. The hot gas can cool down and rain back down into the disk, allowing atomic hydrogen clouds to form. Further cooling permits molecules to form, making molecular clouds, and then gravity will form new stars, as well as possibly new planets in those molecular clouds as the gas cools. So, okay, this is a slide showing a panoramic view of the Milky Way in different bands of the spectrum. And so the center of the galaxy, which lies in the direction of the constellation Sagittarius, is in the center of each strip. So you kind of see this here. And it shows all the directions in the Milky Way disk as seen from Earth. So we can collect information about our galaxy by observing other visible light spectra. So here we're looking at radio waves, where gas is cooled and settled into the disk. Here we're looking at carbon monoxide, showing the locations of different molecular clouds. Up here we're showing infrared emission, and where young stars are heating. Again, some more infrared that's being blocked by gas clouds. We have X-rays, observing from hot gases being emitted, possibly from supernovas, as well as gamma rays. All right, so where do our stars tend to form in our galaxy? A lot of times in a region called ionization nebulae. So the star-gas-star cycle has operated continuously since our galaxy was born, yet new stars are not spread evenly across the galaxy. Excuse me for 1 second here. Oh, come here, buddy. Okay. All right. So there are some regions in the Milky Way that are a little bit more fertile than others. And those environments tend to be rich in molecular clouds where new stars can easily be born, whereas areas that have gas-poor environments do not. So our molecular clouds that we observe in the Milky Way tend to be dark and kind of hard to see. Okay. Okay, so I was talking about ionization nebulae, okay, found around short-lived high-mass stars, very active star formation area. We also have the reflection nebulae. Holy moly, buddy, why are you so mad? So blue and black tints in some star-forming regions tend to have different origins, and we might see a blue color because the dust grains in those clouds scatter blue lights better than red lights. So we call that a reflection nebulae. So kind of the same reason why our sky is blue. I'm just going to skip that slide. Okay, moving on to looking at the disk and the halo of our galaxy. So the halo tends to have no ionization nebulae, which means no blue stars, which means basically no star formation, where our disk is a different story where we do have ionization nebulae, blue stars, and very active star formation. So, child here. Okay. So remember, our galaxy is a spiral disk, so a lot of star formation happens in the spiral arms. We have a lot of ionization nebulae, blue stars, very dense gas clouds. So we just see a lot of star formation in the spiral arms because gas clouds get squeezed as they move in those spiral arms. Squeezing can trigger star formation, and those young stars flow out of the spiral arms. Now the history of our galaxy, the Milky Way, some clues that we find in the halo stars. A lot of times with our halo stars, we find very, very old stars that have a lot of heavy elements. So that means that halo stars formed first and then stopped, whereas stars in the disk tend to be younger. We do see some heavier elements, stars of all ages, disk stars formed later, and they just continue to keep forming. So, yeah, I think that's all I want to say there. So how did our galaxy form? This is a very simplified version. It formed from a cloud of intergalactic dust. Halo stars formed first as gravity caused the gases to contract. The remaining gases settled to the spinning disk, and then stars continuously form the disk as our galaxy grows older. It's a very, very simplified model. Now the final question I want to answer is what's at the center of our galaxy? So the center of our galaxy lies in, again, that direction of the constellation Sagittarius. And the region of the sky doesn't really look special to us when we just look at it with our eyes. However, if we could remove that interstellar dust that blocks our view, we would probably see some pretty cool things. And we hypothesize that maybe a gigantic black hole with a mass as great as 4 million times the mass of our sun lurks within the bulge of our galaxy. So when we look at the center of our galaxy we see pictures like this, and it kind of intrigues us as to what's going on here. So stars appear to be orbiting something massive, but it's invisible. And like I said, we hypothesize it's a black hole, a mass of 4 million suns. And we've also have looked at X-ray flares that are being emitted from the center of our galaxy. So yeah, that does it for our galaxy. Okay.